This next video will concentrate on both sections 7.3 and 7.4, but you'll notice 7.3 is a pretty quick section that we'll go through fairly quickly, give us a few basic ideas to kind of get our brains thinking, but then we'll really start to implement these ideas in section 7.6 when we fully discuss the normal bell curve. So most of this video will focus on section 7.4, going back, thinking about the probability distributions for discrete random variables, and then finding some very specific values, the mean and standard deviation. But first things first, let's start with 7.3. 7.3 gives us an introduction to a probability distribution for a continuous random variable. The previous video in 7.1, we discussed the difference between continuous and discrete random variables. And again, the 7.2 video, we focused on the discrete. When we only have so many whole number values, and when we make the distribution chart, we can literally list every single X value, every single possible answer that we have received or that we could receive, and then give the probabilities for each. But when we have a continuous random variable, now when we start introducing the possibilities of fractions and decimals, there's just too many things to list. Even if our interval is tiny, if you put all the fractions and decimals in, we would have an infinite number of X values. So in this situation, instead of making an P of X and making a probability distribution chart, instead, we look at what we call a density curve. A density curve seems like a fresh idea, but we've actually been doing this for a little bit now. When you go back and look at our empirical rule work, we talked about first that our data needed to be normally distributed, and we'd end up with this type of a bell curve, and that we would actually look at the percentages as the area under the curve. That's exactly what this density curve is all about. Now, they're not always the normal bell curve, and it's worthwhile just quickly reading through this section to get the idea, but the basic picture is, again, that now when we start thinking about probability, well, this curve is supposed to represent everybody, every object in our set, every data value that we receive, and they're stacked accordingly. And the idea of this one being normal had a lot of properties, one of which is that the mean is right in the middle, and that coincides with the median, and that we have this nice symmetry. But the overall idea is that we've got a lot of people in the middle, and then still lots of people as we start getting smaller and slightly bigger values than our mean. And then the further we go away, the fewer people or objects that we have. So really quickly, if we think about this with respect to height of men or women separately or collectively is a nice normal distribution set. And if we look at the average height of men is 5'9", and that's where most men are. But if you go to 5'8" or 5'10", you still get a lot of people. But when you start getting further and further away, how many men are 5 feet tall? How many men are 6'8" tall? You're getting fewer and fewer the further you go away. But in this setup, that if we find the area, that will get us to the probability. And again, we will do all this again in 7.6 or remind us of this, but we've kind of already seen pieces that when you apply the empirical rule and said something like 68% of the people of the data values fall within one standard deviation of the mean, well, if 68% of the people do that, that means there is a probability of 0.68. We've already seen that back and forth with basics of probability. If there's an 80% chance it will rain tomorrow, there is a probability of 0.80 that it will rain tomorrow. So we're going to see more of that, and that's what I mean. We've kind of already seen aspects. Good idea to read, kind of reestablish some of those ideas, but we'll come back and see a lot more of that. So again, now, the rest of this video, we're really moving into section 7.4. And 7.4, we're going back to the discrete distributions, and we're going to talk about finding both the mean and the standard deviation. And again, we'll do this for a discrete probability distribution. Well, first things first, just some of the basic understanding, some of the terminology. If we talk about the idea of a mean, well, we've already kind of got some of the synonyms in earlier sections. We talked about the idea of what's common, what's average. But now we also have to get to the idea of what is expected. That if we hear the words expected value, the expected value from a data set. Okay, we look at all these people and how many siblings they have. So what's the expected number? We look at all these people and how many electronic devices do they have? Well, what's the expected number of electronic devices? If we are working in quality control and we are checking for how many of our light bulbs that we've made are defective, well, we check a batch of 1,000. What's the expected number of defective light bulbs that we will find? So that's the biggest thing, to get used to that expression, expected value, and to get used to that in any context. So that when we hear that, we know when we hear those words, find the expected value, find the expected number of siblings, find the expected number of hours of sleep. All those are basically telling us with a synonym the idea of find the mean. So all that is the mean. We use some slightly new notation for this. For expected value, you will see this E of X, the expected value for a random variable X. So that's the same X we were using before, but that is also our mean. And here we start using the population mean symbol. Once we have that data set, even if we don't have everyone, we can still make predictions based on the expected value for everyone. The book likes to throw a subscript X in here. That's a little unnecessary. Just again, making the connection, expected value is the mean. The formula for this is not that bad. Not quite as nice as our standard formula, add all the data values, divide by how many you have, but it's a very similar idea with the understanding of probability. What we will do, we will take each possible outcome, every value for the random variable, we will multiply it by its respective probability, and we will add all of those values together. So we are going to take the summation. I like to stick an extra bracket here to make it clear. We're going to find the summation of the x times p of x column. So I'll come and use this in just one moment. But let's also, while we're here, let's get right to the standard deviation. The mean still talks about what is expected, what is average, what is common. The standard deviation still refers to the spread of our data. Okay, we know it's in the middle, but now how spread out is that? If we expect that people have 2 TVs in their house, well, is the standard deviation 1/2, so that most people have about 2 TVs? Is the standard deviation 2, so that we have some people with lots of TVs, but some people don't own a TV? So again, the standard deviation still tells us about the spread of our data. We will still use the sigma for our population standard deviation. And just like this formula, when you really understand the ideas of probability, this is a modified version of basically adding up all the data values and divide by how many there are. And that's what's going to be similar here. We'll use this as a separate formula, but in reality, it's just adding in the idea of probability to the formulas we already had. So this formula, we're still going to end up with a square root, and we're still going to get an ugly summation here. We're going to get the summation x minus mu squared, very similar to what we used to have. X minus mu, each data value minus the mean, then we will square that value. But we don't just sum here. We'll now take that times the probability. Once again, the book doesn't put these extra brackets. I think it's a very good thing, though. So we'll have to make this very big, ugly column. Then we'll add all those values together, and then we will take the square root. So just like the mean and standard deviation that you had on test 2, it's much easier to find the mean than it is the standard deviation. And even just looking at the formula, even if you were just asked for the standard deviation, you're going to need the mean first, whether you're asked for that or not. Okay, so let's jump right in. And for this first problem, I want to use something we already had. In the 7.2 video, we did a little problem where we made a probability distribution chart for the number of hours of sleep from a bunch of students. So let's just jump right back into that. So we are now given a probability distribution for the hours of sleep last night by a bunch of students. What I'm trying to do here, everybody, I'm trying to jump into this. After we finish this problem, I'll come back and start a new one completely from scratch and then make a few quick points before we move on here. So we were already given this. Look back, you could look at that video and see how this chart was made in the first place. But now we are just being handed this. So X is the hours of sleep last night, and we receive answers, responses of 5, 6, 7, 8, and 9. Then the probabilities, well, we had to do a little bit of work to figure those out. We had how many students slept each of these hours. So we looked at the total number of students, and then, well, 23 out of the 137 slept 5 hours. So that's the probability one student sleeps 5 hours. And then we keep going. We had 38 over 137. And then we had 43 over 137, 18 over 137, and then finally 15 over 137. When we made this chart, I pointed out that you certainly could have used decimals. There's nothing wrong with the fractions here, but it's not a terrible place to use decimals either. But I'll just leave it the way we had it before. So now, I gave you all this. I still didn't even ask a question yet. Just wanted to get us back on track where we were. So now let's have two questions. Let's find the expected number of hours of sleep that one student had. That'll be question number one. And then question number two, let's find the standard deviation for the number of hours of sleep last night. Okay. Notice, as we were kind of hinting at before, you'll really, really rarely see someone say find the mean in this type of situation. But that idea of expected what? Expected number of hours of sleep. Well, that's the variable that we're focusing on. So again, that's just something we have to understand. That's really telling us find the mean. So here's my formula. I've already got x and p of x. I need the x times p of x column. So I'm just going to go right here. Just extend my chart just that tiny little bit. X times p of x. Now, if you already have these as decimals, that's fine. But even as fractions, how do you multiply whole numbers times fractions? Well, your calculator knows how to do it. Just do 5 times 23 divided by 137. You don't have to do anything fancy here. But now we're going to start getting some messy answers. So again, good habits. We're not done here, so let's try and keep several decimal places, and then at the very end, we'll round our answer. So let me get started here. 5 times 23 divided by 137. Oops. So again, I'll take a bunch of decimal places, 0.8394. Even though, again, this goes on too far, I'm going to have to cut off somewhere. I don't want to carry 12 decimal places. But even when you cut off, don't just cut off, still round. So if I go to here, I'm looking at the 1 and I'm rounding down. So I'll take the 4 decimal places, 0.8394. Keep keep going. 6 times 38 divided by 137. Again, just like we saw before, these are a little computation heavy, so just get some good practice with the calculator. These are not probabilities, everybody. I know in the previous video I was stressing that when you get your P of X column, they are probabilities, fractions or decimals between 0 and 1, but now there's no reason. This happened to be a decimal less than 1. No reason to expect that here. So I'll keep the, again, 4 decimal places, 1.6642. Keep going. 7 times 43 divided by 137, 2.1971. Again, I'm rounding. Eight times 18. So 1.0511. And then last one. So 0.9854. There's the column that I wanted. There's the x times p of x. We've got the full column. Now I will add this. And as soon as I add this, that completes the formula. That's got everything that I had here. That will be our mean. So I'll just finish up my work here. And now, there's my answer. Now I could think about rounding. We're talking about hours of sleep here. That was the units, I should say, for all these x's. So just like we kept seeing with mean and standard deviation earlier, a couple of you lost a point or two here and there on the test, still keep the units. Are we still talking about, time to complete the puzzle in minutes? Keep your values labeled minutes. How much people weigh in pounds? Keep your values labeled pounds. So all these are hours of sleep, so this still represents hours of sleep. So I'll take one decimal here, and we'll say 6.7. So coming back over here, the answer is we'd have an expectation of 6.7 hours of sleep. Now, expected value, we never had any decimals here. This was a situation we kind of forced this to be discrete, even though sleep time would be continuous. But the way people gave their answers, we were able to treat it as discrete. But there's no reason to round this off. Yeah, that's about 7. But for any further computation, we don't want to round too far. The next step, when I start doing the standard deviation formula, when I start subtracting from the mean, don't round this too far. I will use the 6.7 here. So let's get to work. I kind of ran out of space here, so let me kind of just quickly recopy down here. So I've got my x, my p of x, so I've got my fresh column starting all over again. I could extend this. I just ran out of room. That's all it is. But now, going back to my formula, x minus mu. Each x, we're not even using probability yet. I'm taking x. We've got that mean right here and right here is 6.7. So every x value minus the 6.7. 5 minus 6.7 is negative 1.7. 6 minus 6.7 is negative 0.7. 7 minus 6.7 is positive 0.3. 8 minus 6.7 is positive 1.3. 9 minus 6.7 is positive 2.3. Okay? Now we will square, right? X minus mu squared. So now I've got the x minus mu column. So now my next one, square all of these values. This is very similar again to the standard deviation that we did on the last test. Some people, instead of filling in the whole column, they just jump right over. I was doing this arithmetic in my head, but maybe all at once. You do 5 minus 6.7 equals squared, and I get my 2.89. And I'll keep doing that. So maybe I filled in a cross instead of doing all of this, then doing all this. But either way, that's the direction. We need to get this whole chart set up. Oh, I should have pointed out just a few minutes ago, everyone. When we had our answer here, notice the answer makes sense. And even just looking at our ballpark, we're looking at people. Some people only sleep 5 hours. Some people only sleep 9. But most people were down in here, right? That's where the biggest number of people, these were the highest probability. Not too surprising, that's where the mean was. You know, if we ended up with a mean of like 4.1 or 10.7, I mean, that doesn't even make any sense. We didn't have anybody sleeping that little or that much. So definitely in this type of problem, just looking at the X values we have, that average should make some sense. But realize it was not so easy to just say add these X's and divide by 5 because there's 5 of them. We had to take the probability. These were not all equally weighted, so that's why this formula had this little extra bit too. But now again, coming back over here, let's finish filling this in. So again, just like I was showing you, I'll pretend like I started from scratch. 6 minus 6.7 squared, and I get 0.49. 7 minus 6.7 squared, and I get 0.09. 8 minus 6.7 squared, and I get 1.69. And 9 minus 6.7 squared, and I get 5.29. Last one. This is where we will finish. This will be the last column. It wasn't just x minus mu. It wasn't just x minus mu squared. It's x minus mu squared times p of x. So this is typically how our columns are set up. But notice, I hadn't used the p of x yet. Now I'm going to. Now to finish this, x minus mu squared times p of x. This is the last column. I'm taking this value times this probability, and that goes here. This value times this probability, and that goes here. That's how I'm filling in this column. And now you could see, everybody, if you already made these decimals, maybe that shortens a little bit of work, but there's no problem leaving these as fractions for this type of setup. Because now when I just do the arithmetic, I just input them as fractions. So again, back to here, 2.89 times 23 divided by 137. And again, lots ugly answer, so just like we were doing back here, take a bunch of decimals, we'll do our rounding at the very, very end. So I'll do 0.4852. Just trying to get a bunch of decimals. You want to take more, go for it, no problem. Just don't take too few. If you only take 2 decimals now, again, you're just doing too much rounding. So keep moving it along. Now I'll take the 0.49 times the 38 divided by 137, 0.1359. Very computation heavy, everybody. You really don't have too much knowledge about what these decimals numbers should come out to, so we just want to be very methodical. Keep going. 0.09 times 43 divided by 137, 0.282. 1.69, 18 divided by 137. And finally, 5.29 times the 15 divided by 137. There. That's what I add together. All of that goes in place here. So the summation of this whole big column and a lot of ugly work here. I really just want to go back for a second. Just again, either I do it twice or I just be very methodical, make sure I didn't accidentally miscopy anything, have an extra decimal place. All those little things could easily happen. So I got 1 point. And now I need the square root. So my standard deviation will be the square root of that summation and now I could round. So just like before, I rounded the average to the 10th hour, so I'll do the same thing here. We would have 1.2 hours of sleep. Again, I want to do a whole problem starting from scratch, making the probability distribution chart, and including these questions. But in any of these situations, we have some real context to check our answers. To again, think about the mean, think about the standard deviation, and realize that it makes sense. We explained why the mean looked good when we started thinking about this, but now realize the same tricks we've always used. Think about the mean, 2 standard deviations above, 2 standard deviations below, and that should basically cover most of your data. Well, if you subtract the standard deviation twice, you would get 4.5. If you add the standard deviation twice, you would get, what is that, 7.9? You would get 9.1. And you've covered everything. That really should make us feel good that we did these correctly with all the little places for mistakes. But once we kind of see that at the end, if you got the standard deviation as 10 hours of sleep, that's ridiculous. That is way too big of a spread, especially when you start considering the whole ideas we've been establishing. Most values fall from 2 standard deviations below the mean to 2 standard deviations above. So, moving on. Like I said, let's do another one. And let's start it completely from scratch. Certainly realize, as far as test questions, don't do everything, do what I ask you. If I just ask you to make a probability distribution, go ahead, make it. If I give you a probability distribution, we should be able to answer questions about mean or standard deviation. Maybe I ask you for all of it, and that's what I'm going to do here. So make sure when you're reading the problem, you should be able to handle any piece. Just making the distribution, or being given a distribution and being asked to find mean, standard deviation, or just being asked to make the distribution and find the mean. So again, make sure we're only doing what we're being asked to do. So now let me again set up a whole big problem. So we survey a bunch of our neighbors asking how many televisions, how many TVs are in your house. We receive the following answers. We have 13 neighbors do not own a television. Then we have 21 neighbors own 1 TV. 37 of our neighbors own 2 TVs. 23 of our neighbors own 3 TVs. And finally, 7 of our neighbors own 4 TVs. So look back to the 7.2 problem, very similar beginning. And I hope you're starting to notice everything in chapter 6 and 7, you almost always have a lot of buildup, a lot of description. What is the question? What are we looking to do? Well, we always have to read through carefully to evaluate. What is the actual question? What information are we being given to start to formulate how we're approaching it? So right now, all we have is a lot of information, no directions yet, but here it's coming. So several things we're going to do. Number one, first, we will make a probability distribution chart based on the number of televisions. Based on the number of televisions in the home. Number two, we will find the expected number of televisions in a neighbor's house. And then number three, we'll find the standard deviation. Just like we keep saying, there's really no way to hide asking for the standard deviation. There's no other synonyms, there's really nothing else to say, so that one's pretty obvious. However, it really should be more clear, the standard deviation for what? The standard deviation for the number of televisions. So we're being asked to find everything here. So we start getting to work. Okay, I've got all this information. First thing, making the probability distribution chart. So I'm going to get myself set up here. I've got my X and my P of X. This will be the chart, but I'm just already preparing for the second parts where I'm going to need those extra columns. But this is the chart. That's it. When we made basic frequency tables, we needed all the categories and the frequency. We may look for other things. There may be relative frequency. There may be other things we do when we're asked for other values. But that was it for the basic frequency table. All the different categories and the frequency. And similarly, that's it for the probability distribution. All the X values, all the P of X. Well, what's X here? We're talking about the number of TVs in a home. So this is not X over here, this is X over here. And when we start, it's easy to start saying, doesn't matter the order, just to get them all here. It's nice to put them in order and be methodical while we get them here. But to realize, we're over here. These are the number of televisions. And if you don't own a TV, well, that's the same thing as saying you have 0 televisions. But then more straightforward after that, people own 1, 2, 3, and 4 from the information we were given. What about the probability? And this is what we said before. It's easy. Some people just think, oh, there it is, and they just start filling in these numbers over here. But that's not how it works, because we need probability. So the probability, you have 0 televisions. How many people have 0 out of how many total people that we have? So I need to do a quick total here. If I had 13 people here, then 21 here, then 37 here, 23 here, and 7 here, that means I interviewed 101 of my neighbors. Again, everybody, I could have been a little nicer and made this out of 100, try and make our decimals a little nicer, but we shouldn't expect that. So that's why I'm very comfortable. The last one we had divided by 137, now over 101. But that's fine, everybody. There's nothing wrong with that. So now we start filling in the probabilities. 13 people don't own a television, so there's a 13 out of 101 probability that you own 0 televisions. Similar, a 21 out of 101 probability that you own 1 television. 37 out of 101 that you own 2 televisions. 23 out of 101, the probability that you own 3 TVs. And 7 out of 101, the probability that you own 4 TVs. So now we could really focus just on the chart itself. So my formulas, that's part 1, you're done. That is the probability distribution chart. If that's what we were asked for, we'd be done, nothing more to do. But I did ask you for the expected number of televisions. Again, to realize, that's really saying what is the mean. So from the previous sheet, X times P of X, that's what I'm doing. So I'm going to go right into that column. My next, I'll make an X times P of X, this times this. And I'll take care of this first one. 0 times anything is 0. And I could kind of keep doing that. These are not the worst. I could still keep fractions here, everybody. What's 1 times 21 over 100? It's 21 over 100. What's 2 times 37 over 101? 2 times 37 is 74, so I get 74 over 101. So I could, but I just think at this point, because we're not expecting to get nice decimals here, so when you start multiplying, things start getting ugly. I think most people start really going for the decimals is the common thing. So again, take a bunch of spots. I'll take the 0.2079, then 2 times 37 divided by 101, 0.7327, Again, realize I'm rounding. I'm not just cutting off at the 6. I'm rounding from here to get that. There's my x times p of x. Mu is equal to the summation of this column. So I would add all this up. And now I could round. This is my final answer. So 1.901, again, good sense. How many televisions? We definitely want the whole number, but certainly taking the first decimal. We're basically looking at about 2 televisions. Not too surprising. Just like before, the 6.7 hours of sleep, really right in that middle area of our data received, and that kind of is a similar situation here. So we'll have 1.9 TVs. You can't actually have 1.9 TVs. Again, roughly, we talk about that's an average of 2, but for further computation, we want to leave the decimal. And that further computation is coming up right now. There's my answer to part 2. Notice again, I included the units. I got 1.9 TVs for the final answer. But now my standard deviation, again, use the 1.9. Now I'm using this formula. Even if I didn't already have the mean, I needed to use this formula. And now my chart really looks ugly. Here, I kind of made this part of my chart to get my mean, but then I restarted to get my standard deviation. More commonly, you're just building off of the same chart. So I just keep going across, but in the same way. I'm going to need x minus mu, which again is really 1.9 for the mu. Then I'm going to square those values, and then I'm going to take those values times the probability. And now that we're really doing this a second time, I can really, again, I could fill in all this, then all of this, then all of this, or I could just move directly across. I already have the 0 here, x minus mu. So I'm getting 0 minus 1.9 is negative 1.9. But then that negative 1.9 gets squared. Oops, sorry about that. I need parentheses there. That's why it was nice when I was doing all the work. When I just hit answer squared, it knew the negative was a part of my answer. So that's positive 3.61. Remember, you're squaring. Everything will always be positive here. Okay? So 3.61 times the probability. So times 13 divided by 101. 0.46. And just like we were saying here, keep a bunch of decimals, we'll round at the end. Keep a bunch of decimals, we'll round at the end. So now, right from the beginning, 1 minus 1.9, negative 0.9. I could have done that in my head, but just to get it in the calculator, squared, show you how I'm just moving across. Because the positive 0.81 times the probability. And do it again. 2 minus 1.9. I get 0.1 squared. 0.01 times the probability. So I hope this is very clear. You could see this is definitely a little time consuming. There's definitely a lot of little tedious work here. And the nice aspect is now with the take-home exams, you do have a little more time. But as we always say, it's good to get a little practice here. You don't want to take a half an hour to do this, but certainly to take a few minutes to be very methodical. And now let me finish that. I got 2 more rows to fill in. And last one. That's 4.41. So now I will take the summation of this column I don't want to round off here. Just to remember the last part of the standard deviation formula, I still need the square root of that mess. So that's my last line. The square root of 1.2179, the square root of this previous answer, and now I'll round off. And now this 1.1 still represents TVs. Go down the standard deviation twice. You go a little, you get a slight negative, go up twice, you'd be just over 4. And once again, we see this mean with this spread covers. Doesn't have to cover all of it. These are just simple enough examples that we're completely covering, but we should always see we at least get most of these values. The last thing I just want to say, to finish up this video, 7.4 is a very nice section, but 7.5 and 7.6, those are going to be very, very big ones. The other quick thing before I jump into that, I want to point out, this starts to give us a little bit of an introduction to what we call game theory. That you could play situations, like if you go to Atlantic City and want to play roulette, or if you are entering a little raffle, how much money are your tickets? What are the prize values worth? You could figure out some expected value there and start talking about fair games, that casinos are favored, that you are expected to lose money in different rounds. So we could do more examples like that, but that I think gives us a very, very good overall introduction and some very basic problems to follow. The last thing I want to do here is give you a super fast introduction to 7.5. 7.5 is a pretty lengthy section. It's a lot of computation there. So I just want to give you the most basic introduction. When I make a full video on this, we'll go over these things again. But if you want to just jump ahead a little bit, start to get into 7.5. 7.5 goes back to discrete distributions. They also talk about something called the geometric distribution, but the binomial is the main one. They start off with this description of what is a binomial experiment. And there are several things we want to say here. So again, this will be very quick. Just if you feel comfortable and want to get ahead a little bit, still worth listening to because this will be a big section. So a nice introduction, but we'll cover this again when I do the 7.5 video, and we'll get problems to go with this. So the binomial experiment is an experiment where trials are repeated. Each trial can be considered to have 2 outcomes. We will formally call those outcomes. One of them we'll call success. The other one we'll call failure. Sometimes failure is a little too strong here. It doesn't really mean we failed. We just didn't get what we wanted. If we're rolling a die and we want a 5, well, rolling a 5 is a success, and rolling anything else would be considered a failure. So it sounds harsh, but it's really just not getting whatever it is that we want. That the probability of success and failure, are the same for each trial. When we put all of that together, we will end up, if we have a situation that is binomial, we will get this very nice formula. The probability, now we'll use x as the number of successes. The probability of x successes will equal NCX. N will represent the number of trials. I'll come back and explain this notation just a little further in just a moment, but we'll get NCX, where N represents the number of trials. X is, again, right back to here, the number of successes. We will have little p, and little p will be the probability of success, but only in one single trial. And that will be raised to the x power. So the probability of success raised to the power of how many successes we want. This is where my notation is slightly different than the books. I then use a q to come next, a little lowercase q, and q will be the probability of failure in one trial, and that will be raised to the n minus x power. So what that boils down to, again, I will come back and basically prove this formula. It's not a formal proof, it'll be through an example, but we're really gonna see just how we have to get used to this formula, and we'll get a lot of problems to see examples of binomial experiments and to get more practice using this. But in general, we're running so many trials. How many successes do we want? What is the probability of success in one trial? What is the probability of failure of one trial? We plug all this in, and that'll give us the probability of this many successes in this many trials. This is the real new thing. So that's why I just wanted to at least get to this here. How do you do this? Other books, when we do our basic probability, get a little deeper into counting and get a little deeper into this idea. Our book just kind of throws this at us. They even use some other notation, but I just want to show you on two calculators so you could already start looking for this. So I will show you on this calculator that if you want this button, you have to go under the stat option. The math option. I'm so sorry about that. First we click math, and then across the top, we have to scroll over to PRB. PRB stands for probability. And number 3, that is, they're using an R here instead of an X, but that's the same notation. So let me just quickly show you one value. If I wanted, let's say, 10C3, on my calculator, I would have to first start on my blank page, put in the 10, then math, then scroll over to PRB. I could either click number 3, and that'll give me the NCR, or scroll down and then click enter, and then I'd put in the X3, and then I'd hit enter, and that equals 120. This is really talking about, again, counting. If we have 10 objects, how many ways can we rearrange those 10 objects, picking 3 of them? That's a little bit of the deeper understanding. And again, I'll re-explain that in the next video. But just trying to show you how you compute that. A lot of you have a calculator more like this one. And if this is your calculator, you've got that button. Oh, where is it? So. I'm sorry, here it is right here. I've got the PRB. A couple of you, if you have an older Texas Instruments, you'll just see that NCR just above a different button. You'll just see it as one of these second options, just something that's highlighted. But a lot of us have this other. We hit the PRB button, and there is the NCR. We just scroll over, hit enter, but just like we saw in the previous, I'd have to first put in the 10, then I'd hit the PRB, then I'd highlight and hit enter, then I'd hit 3, enter one more time, and there's the same 120 we had a moment ago.